Welcome to this next lecture on examples in mathematical oncology. Previously we have worked on some of these growth model for cancer cells, and now we're going to incorporate something that occurs quite often when we are talking about these sort of processes, which corresponds to some competition process between some healthy tissue, or namely normal cells, and cancer cells in between, right? So in this case we are going to consider the following example. Consider that there's a system. We could think of, for example, the colon crypts and how cancer can stem from there, and consider some stem cells that produce this healthy tissue, these normal cells, that they just go on and function normally. But there are some stem cells that actually are cancerous stem cells, and instead of producing normal cells, what they do is they produce cancer cell types, right? And what we're going to look at is what's the situation that we are going to encounter, dynamically speaking, when these two types of cells are actually competing. They could be competing for nutrients or for space, in whichever case. And now we're just going to try to work out what's the dynamics of this process. So, just as we've done before, what we have to start with is by considering the different ordinary differential equations that are governing this system. These are going to be our two variables of interest, and we're going to consider them as follow, right? So there's going to be two differential equations here, up and below, and in the first hand, we're going to have that this sector of the population here, the total number of healthy tissue, normal cells, is being fed by the number of stem cells, which we will consider to be constant all along the problem, and it does so at this given rate. Right? So this is the rate of production of these normal cells. And of course, this is coupled to the actual number of stem cells correspondingly. On the other hand, we're going to have something exactly equivalent for the cancer cell types. All right? So far, so good. But now we have to include this competition term that, as we have studied in previous lectures, it comes as the following form, right? So here we're going to have a depletion form, a depletion term. That's the minus sign that's coming from. We have studied this before, so I'm going to just go ahead and jump to what is the form of the functional form of this thing. Okay, and now we're going to comment further. And we coupled these two terms to a particular function phi that we need to extract from some constant population constraint. This is the constant population constraint that it's going to give rise, right? In this case, we're going to take it to be just like this. So consider this is normalized somehow by the total number of cells that are in that specific system, and we set this to 1. And this condition is what allows us to extract the values, or better said, even the functional form of the phi function. Right? How did this work? Just to remind ourselves, what we do here, the trick is to take derivatives over time on both sides of this equality over here, right? So if we take derivatives over the left-hand side here, using the dot notation, what I'm going to have is this, but on the right-hand side, this gives us a 0. Since this is a 0, but I do know what's the functional form of both these terms, because I just obtained them over here, I could go up here and write this equation again, right? So I'm going to do it like this. This is going to be the first term, this n. Sorry, there's a minus sign here. Right? And the next term is going to be simply this other one. Sorry, my mistake. This is the number of stem cells of a cancerous type. And this is equal to 0. Now, very simply, we can just move forward and quickly say that n plus c, which can be taken here as with factors phi outside, this is going to again be summing up to 1, which basically allows me to obtain this phi function very quickly as follows. Okay, so now we can move on and solve, for example, for C. Let's we're going to write down again the ordinary differential equation that's governing the number of cancer cells over time, and we're going to utilize this solution that we obtained, right? So I'm going to square this, and I'm going to use it right here. Right, so let's just rewrite this and make the following observation. Now consider this is going to be C, right, this variable that it's sitting here, but now I can substitute for the whole thing. Oops, again, sorry. Okay, this is the stem. I'm always confusing this. All right. So this is an ordinary differential equation that we are now capable to solve because there's no couplings. If you notice on the right-hand side, all we have are constants plus our function of interest, which in this case we have taken to be the total number of cancer cells. Notice that if I am able to solve this problem, thanks to the constant population constraint, I am also solving the complementary one. I can also always substitute the total number of healthy tissue cells, the N, I can substitute when I have the value for C, right? So by now working only on this equation, I have all the information that I would require eventually. We're going to solve this, but not over time, because we have done this before, and this is something that you could do as an exercise yourselves, but actually move straightforwardly and get the corresponding fixed points and understand its stability. So very quickly, remember that fixed points are going to arise as soon as I determine that there's no further evolution, no further time evolution for this dynamical variable, in this case C, which leads us to taking this function here and equating it to 0, basically looking for the roots, and very simply we can see that for this specific case, and that's quite easy to do, we obtain the following. Again, like this. All right, so now we have our fixed point, and we can also look at its corresponding stability. But instead of going for the usual way, which is looking at the Lyapunov coefficient and asking how this is valued, either positive or negative, what we're going to do is just moving straight forward to compute the potential function. So we're going to compute the potential function. Remember, this is our f of c, if you like, right? And we have to integrate it and add a minus sign to it. I'm just going to do it straightforwardly because now we are quite used to doing these sort of operations. And I see that what I have to be careful with is trying to map this correctly with all the appropriate minus signs. Okay, so here I'm going to have a term that it's squared, that's going to give me a sort of a parabola, right? And then I'm going to have all these terms right here, which are quite cumbersome. But in reality, this is a very simple function, right? So here I have a linear term with a minus sign, which means that as I want to plot this, right, and I am close to 0, the 0 value, that would mean no cancer in this case. Well, what I know is that this is going to be the leading term, and this leading term actually comes with a minus sign, therefore I'm going on this downhill trajectory, at least for low values of C. But as I move onwards to the next term, okay, which is this squared one, I know that this is a parabola which branches are pointing upwards because of the positive sign, which means that eventually as I move onwards on the C axis, this is going to look like this. And it's going to pick up pace and it's going to be resolved as a parabola, right? I don't need to worry about the non-physical values of C, and all I need to look at is just from this simple computation of the potential function that there will be a minima right here. And naturally, this minima will, of course, correspond to the fixed point that we have calculated just before. And one can also argue, why is this? But it's pretty much straightforward, right? And basically that's the end of the story. If you think about it, here we have a stable solution. This means that this system will stabilize towards this value, and very quickly one can compute what's going to happen for its corresponding total number of healthy cells, or normal cells in this case, and it typically is going to give you this solution. So you can do this yourself by the trick that I've mentioned before. And the only thing remaining here to comment on is that if you consider that there will be some features, such as it could happen that this is one of the features that basically corresponds to this cancer type, and it's basically the idea that it produces many more of the cancer cells in this competitive setup, that the actual normal cells, the stem cells the cancerous stem cells are being way more effective than the normal ones. Then you see that these fractions that we have obtained here, the solution for N star and the solution for C star, are going to be tilted such that in this case we will see that the number of cancer cells is going to be larger than the number of normal cells, right? So there's this equilibrium, this delicate balance between the two, that it's very well captured by this very simple model. All right, great. So in this next example, we're going to look at something a bit more different, that it's extracted from a paper from 1997, which is both an experimental and theoretical paper, where they develop a very interesting model that can be applied experimentally, as I will explain now, to understand how metastases work. Okay. So in this case, what Loita, Lisi, and others did is to take some cancerous cells that they could create and maintain in their own lab, and now inject them into the vascular system of some mice that they were experimenting with. Okay, so these cancer cells are also importantly marked by a nuclear marker that allows it for later scan and see where these cells are sitting, these cancer cells, where they are sitting, and I'm going to explain a little bit more now about that, but also to actually know the total number of cancer cells that are still going around into the mice system. Okay. Now, what is the model that we're going to use in order to model this exact experiment, this precise experiment? Well, consider that we have an initial inoculation, okay, of n sub naught number of cancer cells that we include into the vascular system of the mice. What can happen then? Well, these cancer cells, in particular, what they did and what they were designed to do is to go into the alveolar tissue, okay. And this is a depiction of how the alveoles should look like in the lung. And because these cells are traveling through the vascular system, they could actually, two things could happen, right? And this is how the model is constructed. Either these cells get arrested, that's how they define this, which means that they reach these alveolar areas, but they do not penetrate to the tissue. So they do not start metastatic foci, right? And in this case, they can stay arrested for a while and eventually decay via different processes, right? We will consider a decay rate for these arrested cells, which we are just going to call it delta sub A. But eventually, sometimes, some of these cells, right, with some probability that we call P, they actually become metastatic cells in the sense that they are able to penetrate the wall and incorporate themselves into the alveolar tissue. Right? These are going to then stick around there, and they will have a different decay rate, namely delta sub m. Right? Now these cells are now incorporated in the alveolar tissue. That's the only two compartments that we need to consider, and we are going to basically try to solve what should the curve over time of the total number of cells look like, right? So if we were able to now map through this nuclear marker, how many cells am I seeing, either if they are inside the vascular system or they are already occupying some positions inside the alveolar tissue, we would like to know what's the overall number of these cancer cells that we have included into the system and how they decay over time, right? Okay, let's do it. So first off, we need to think about what, again, are the ordinary differential equations that are governing the system. We have two variables now, which is A and M. Consider that, of course, N naught is going to be constant. It's just an initial inoculation. And therefore, we want to start by looking at what's the change of rate of the arrested cells, the ones that do not penetrate the tissue. Again, we said, well, there's going to be some decay rate for A, right? So we can just do it like this. And there's going to be some of these arrested cells that actually are able to penetrate the tissue and become metastatic cells. But this happens with probability, and let's actually use the word rate for this value. This happens at rate P. But again, this means that these cells are not now being depleted from the system, but actually they are going into this other sector of population, right? Again, this is going to include a minus sign. Right, let's move then for the total number of metastatic cells. And we see here that the first thing that appears is that all the arrested cells that are able to penetrate the system, they will become metastatic cells. Therefore, I have to include this term to begin with. The next term, obviously, it's going to be something like this, right? Which is the decay rate of these metastatic cells that we have considered to be different from the ones in A. From the beginning also, we have said that this experiment included an initial inoculation of these cancerous cells that now travel through the vascular system. This means that there is some notion of an initial condition. We have to include this initial condition if we are to solve these equations, right? And in this case, what we shall have is that initially, since this inoculation is basically injected right into the vascular system, all the cells that I have started inoculating will be arrested. Therefore, I shall have this initial condition, which relates to this number of cancer cells that I include in the system. Naturally, at the very beginning of this process, there will be no cells that have attained metastasis yet. Therefore, this is going to be the initial condition for the other compartment. We will now solve for both A and M, and then write down what would be the solution of the total number of cells, which here I just denote R, right, over time, which is basically the sum of the two. But in order to do so, we go step by step and start solving these two ordinary differential equations. So let's begin with this one. This one we can do because we are actually pretty familiar with this expression, and let's just rewrite it in a more suggestive way, just taking the common factor. And now we are very much aware what is the solution for this, and we can write it straightforwardly. This is the exponential decay because there's a minus sign in front of it, and since we also know the initial condition, we can straightforwardly write down this solution. Be careful here with the brackets, and we are done. So this is the easy part. We know that the actual number of arrested cells is decaying over time in an exponential way, right? Notice that the exponential, of course, carries two factors. The rate at which these arrested cells are penetrating the tissue, and also the rate at which they are being simply depleted from the system. Now it's turn to tackle this other equation here, which I'm going to do right here. But notice the following. Here in this equation, I do have a coupling with the other population sector, namely A. Therefore, I will have to rearrange these terms and write it in a more suggestive way. In this case, I'm just going to bring the decay term to the left-hand side, and this is what I'm going to get, while keeping this on the right-hand side, but using the fact that I now have the solution for the number of arrested cells over time, and therefore this should correspond. Notice that this is what I'm doing right here. I'm just substituting A for the A that we have in the ordinary differential equation for M, the metastatic cells, and that's all we get. Great. So here there are two ways of continuing onwards with this problem, right? The first is to say, oh, right, so this is an ordinary differential equation which has, on the one hand, an homogeneous solution, right? And then on the other hand, it's going to have a particular solution. I shall start working out the homogeneous solution and then find the particular solution, yada, yada, yada. But we have learned before that there's a nice trick that I'm going to write up here, just to remind ourselves how it works, that allows us to solve these sort of equations, these types of equations, quite straightforwardly. And since we know this trick and we have worked it out as well, we don't have to think much further. Let us remind ourselves here how the trick works. So in general, whenever we have an ordinary differential equation of this type, and here I'm using phi1 and phi2 as general functions of time, x would be our variable of interest. Of course, this is going to map here with m, respectively, etc. And on the right-hand side, we have something that is independent of the variable of interest, so it's independent of x, but it's dependent on time. This is precisely what we had here, right? So whenever we encounter an ordinary differential equation of first order just like this, we know that there's a solution that I shall write it just straightforwardly as follows. So first we'll have to solve some basic integrals and then some other basic more integrals. Let's write it like this. Right, and here I'm going to have yet another integration and some integration constant that shall be fixed by initial conditions. Right, so this is going to be integrating up to t prime, and this is going to be integrating t, and this is also going to be integrating t, which is our variable. Right, so this looks pretty cumbersome and quite scary, but let's not get too scared, because now we can do it step by step, and we'll see that this is actually pretty straightforward from now on. First off, we need to identify, now that we have this theorem in our hands, we need to identify the different terms here. As I said before, x, of course, will correspond to m, the total number of metastatic cells, right? Phi1 of t, notice that it's actually a constant function. In this case, I could say, oh, this is my phi1 of t. Great. So this is a constant function, and I notice also that in this expression I'll have to integrate it over time, but that's quite easy, right? Because if all I need to do is, let me write it like this. All I need to do is this, but for this specific case, this works like this. Well, this is just delta m times t. So these two integrals that I see on top of the exponents in the arguments of the exponential functions, both here and here, although here there's a minus sign, this is going to be just simply delta m t. So something is already quite done. Let's just now, using this fact, rewrite how the solution of m over time should look like given all of this, right? And then we'll fix for initial conditions. So let's do it over here. Now I'm using all of this knowledge, all right, to write down almost the final, the general solution for this. So first off, I'm going to have e to the minus of this integral that I've solved. So this is going to be e to the minus delta m t times this integral here that I shall write a bit more specifically now. Right, so this is going to be like this, and we have p n naught. These are constants, they can go away, they can go not away but outside of the integral. Notice that there's an exponential function here, which is now going to be to compose with this other exponential function, which argument we already know, it's just delta mt. Be very careful here with the signs, because there's no sign in here, and there is one over here, which leads us to the following. And we shall write it just like this, okay? This is the variable that we now need to integrate. Finally, there's going to be an integration constant that we shall fix just at the end. Okay, so this is our integral. Again, as I said before, these two terms can go outside of the integral. That's pretty straightforward. And this requires some denominator that's going to appear. So let's just move on and write how this should be solved altogether. Again, here, P and naught can stay outside. And here, I'm just going to take the primitive of this, which if you notice, is nothing but e to the delta m minus delta a plus p, all these times t now, divided by delta m, delta a plus p in this denominator, plus the integration constant. So we are almost there, yeah. And we are almost there now. First off, I need to include this term over here, right? That's going to actually cancel out this positive e to the plus delta mt, if you notice. So this part here is going to go away in virtue of the fact that I have this guy outside. And here I'm going to pick up this factor. I cannot forget about this one. Okay, so we can rewrite this as follows. Let's do this step in between. Okay. All right. And here I shall have plus c e to the minus delta m t. All right, so this is the general solution for m of t, and there's only one thing left to do here. We need to obtain the value for c. Now, how do we do that? Well, we know that we have some initial conditions that we have already used when we were looking for this expression, but we now need to remember for the total number of metastatic cells at the beginning of the experiment. Since at the beginning of we consider the beginning of the experiment, the inoculation time, therefore there shall be no metastatic cells at that specific moment. Which means that I need to now do the following. I need to take this solution that I have here written pretty much, and impose this in order to find the value of this constant. Okay, so I shall erase the blackboard and I'll do it right there. As we've said before, since now we can impose this condition from initial conditions, at time equals 0, there's going to be no metastatic cells, which from the previous equation, this will correspond to the following solution for the integration constant c, right? Well, it's pretty easy to, from the solution that we got before, it's pretty easy to see that this is going to include the following values: minus p n naught divided by delta m minus p plus delta a. All right, so if you don't see this so quickly, please stop and think about it for a second, and you'll realize this is the actual solution, which allows us to effectively write down the full solution for the total number of metastatic cells over time. And in fact, thanks to these terms, we can now take some coefficients off from the brackets, and we shall have something like this. All right, and then times e to the minus delta a plus p t minus e to the minus delta m times t. So this is the solution for m of t. All right. What I'd like to do now, before we move on to the last quest from this problem, which is to add both m and a from before and plot it and check with the actual experiment, I want to think about two specific questions at this point. First off, how this function looks like. How does this look like? Well, we will consider the following. Okay, we will consider that actually delta a plus delta p, plus p, the rate at which arrested cells are becoming metastatic cells, we will consider that this is, for example, larger than delta m. Okay? So this means that arrested cells die quicker, and also they go to metastatic in a faster pace than the pace in general at which metastatic cells are dying, right? So if you're under these conditions, and I ask you to plot what's the total number of metastatic cells over time, well, we have this equation right here, this solution, but notice that there's some things that are not we cannot be very comfortable with. For example, this is now larger than this, but it sits right here in the denominator with a negative sign in between. But we could just move one at each side so that this solution could be rewritten as follows. Right? I could just always do this, but I'll pay the price of a negative sign coming out of this manipulation. However, I can switch this exponent functions here, which carry a minus sign just between, and that corrects for this minus sign that I've generated from this manipulation. Therefore, I shall have something like this. And that's more comfortable to work with, given this condition that I just supposed, right? Now, this is going, under these conditions, this, as it sits here, is going to be a positive number, right? This, at t equals 0, this is going to be 0, naturally, as we have imposed so from before. So we shall start right here at 0 for the total number of metastatic cells over time. But as we move on with t, what is going on here? Well, we know that this is larger than delta m. So this exponent here, which carries a minus sign, is going to be going down faster, right? So this is going to be going down faster than this exponent here, because delta m, precisely as the coefficient for this exponential decay, is smaller than delta a plus p. Therefore, the negative value here is going to go down, right, faster, and the positive one is going to go down, but not so fast. So if you just think about it for a second, and if you're not convinced, please take some values here that correspond to this inequality and plot it yourself. This will entail the following functional form. This is going to go up as this term becomes more important than this one, but for sufficiently long times, all right, for t much larger than 1 over delta m, which is the time constant for this exponential form here, this is also going to go to 0. This will already be quite 0, because this is quite large, and therefore e to the minus something that is pretty large is going to be 0, quite faster than this part here. But eventually all will go to 0, and then we'll have something that looks exactly like this, right? Under the same conditions, it's pretty straightforward to see that the arrested cells from the solution that we had before, which I'll just recall right here, this is just an exponential decay that goes like this. Okay? This, we have to think a little bit more about it, but it's not so hard using these nice little tricks that I have just explained. Okay, now for you, I want you to think at home, I would like you to work on the following cases. Now this one is pretty similar as before, but it'll be a good exercise to argue how the function should look like in order to plot it and so on. So consider now that it's delta m that's larger than this combined two rates. How everything should look again. In advance we can pretty much see that this is not going to change. But what's gonna go on here? What's gonna be the actual time scale that I need to be careful with when I'm looking at its decay? And I'm already spoiling it. This is of course going to decay. And finally, this is an interesting case that I also want you to try and solve and understand, which is what happens when this system is tuned such that this coefficient delta m is exactly delta a plus p. What happens here? Can we still use this solution? Do we have to do something else? Please try to do this yourselves, and you'll see that this is actually very illustrative and allows us to go even farther than this simple solution. Huh? So it's actually not going further, but this is a particular case that teaches something very specific. We have seen this before, so it shouldn't be very difficult. Finally, to complete the exercise, we had to compute the total number of cells, be them arrested or metastatic. Why do we need to compute these? Well, if you remember how we defined the, how Lloyd and Delisi defined this experiment, what they had as an output was the total number of cancer cells that from the initial inoculation that still were around in the mice system, right? In each of the specific mice, right? So this means that either if they are metastatic or if they are arrested, I will get that signal. Because remember, this is a nuclear signal that I can capture out of some scan of sorts, right? Therefore, when I make this model and I work out their predictions, in this case, I'm working out both the evolution of metastatic cells over time and the evolution of arrested cells over time. This is great, but at the end of the day, I really need to work on the total number of cells that I can pick up with my apparatus, right? The fact that there's going to be two compartments, this is going to appear in the solution, but we need to work out this solution. So, as always, when we are doing this intersection between experiment and theory, we need to be careful that theory is going to give us a bunch of tools, but we need to be correlating them to what we are actually gathering with data at each instance. But this is not a very complicated computation. We can just write down what's going to be the solution for this, and you can work it out yourselves. And interestingly, this is going to give this solution. This is going to come here. Notice now that I am writing the denominators with this form rather than the one below. I can always do that. Naturally, this is going to stem from the sum of the two, so you have to sit down, write each of the solutions, which you have already now in the blackboard, and work out step by step exactly in order to get this. No, this is exactly the same denominator. I could have just taken it as a common factor, and then e to the minus delta m t, right? So this is our solution for the problem. So it's quite long. Let's square it. Right? And as a final note, in your problem paper sheet, what you will see is that there is some sort of a function here which carries some data, right? And this is written in linear log, so this is going to be linear, whereas this is going to be in logarithmic scale, okay? And here, what basically they did is they predicted this line using this expression, and they plotted the data which corresponded to it, right? So this is basically how, at the end of the day, after you go through all this trouble, you can actually come back to the experiment and check that your hypothesis, namely that there's going to be arrested cells, and these arrested cells can penetrate the system and become metastatic at a different decay rate, this can correspond to some of your experiment results. Okay, so this is it. Okay, finally, today we're going to discuss one last example. And in this case, we are going to work a very simple depiction of a model that tries to understand how a differentiation therapy could work, right? So in differentiation therapy, what it's done basically is, the idea is to transform back cancer cells. Instead of go there and annihilate them or kill them, the pharmacological intervention here works as follows. You use some sort of drug, namely F here, that picks up cancerous cells and redifferentiates them into normal cell types, right? And it can do so at some rate, some given rate, beta, right? So as long as this drug around the system, these cancer cells pick up the drug and they can differentiate back into normal tissue, right? At the same time, though, because of the instabilities that are sitting still within these cells, it can happen that these mechanisms are triggered back, so there's some back reaction, and this normal cell tissue comes back into the cancerous type, right? So let us now explore, again, from a dynamical systems standpoint, what's underlying these sort of processes, right? So to begin with, we'll have to use our good old ordinary differential equations for both compartments here. Let's start with the normal tissue. So again, we're going to look at differential equation for the normal tissue. We see here that we are so we are generating normal tissue cells out of this interaction between the total number or the drug concentration that's around the system times its effectiveness, right? So we're going to have beta, the pharmacological intervention, and the number of cancer cells that interact with the pharmacological or the drug in this case. Right, so on the other hand, we'll have from this back reaction or de-differentiation back into cancer cell, we will have that normal cells are being depleted in some sense and feeding back the population compartment of the cancer cells. So we have this simple equation for the normal cells or the normal tissue. And what about the cancer cell? Well, as a matter of fact, for this specific system that now should be triggering some alarms, right? This is going to work as follows. The number of normal cells is feeding this population, the population of the cancer cells, whereas at the same time, thanks to the pharmacological intervention, we are losing some cancer cells at this rate. So we have seen these equations before under a different disguise. For example, in the SIS model, right? So in this case, we do not have susceptible and infected compartments in our ordinary differential equations. We have something different, but in spirit, these are really the exact same equations, okay? We have now derived these equations, and we can just move on and try to solve them using some constant population constraint. So this went under the rock here, but what it's important to consider is that there's some limitation for these cells, and therefore we can impose a constant population constraint of the sorts, and normally we'll do it in this way. So the total number of cancer cells, the total number of normal cells, it adds up to some constant value, but we'll take this constant to be 1, sort of normalizing these numbers and making it easier for us to work with the differential equations. Okay, again, this is equivalent to the SIS model, so it allows us to jump and leap forward quite rapidly. And in fact, we are going to investigate what's, in this case, we're going to use the variable n, and we're going to approximate this problem by the following. Well, here we have that C is 1 minus n in virtue of the constant population constraint down there. Therefore, this whole equation, right, can be written as this. Beta n, and notice I'll have 1 minus n in here, right, substituting from the constant population constraint, which means that I can just rewrite the whole thing as follows. And this is skipping one single step, but I'm confident that everyone here will be able to work it out themselves. Right, so now we have a single ordinary differential equation in which either side we only encounter either constants or our variable of interest, and this is something that we can readily solve very quickly. We have seen this before, and we're going to actually only explore its fixed points and the stability of those. Right? Notice that if I work out the fixed points for the normal tissue cells, I immediately know what's going to be the fixed point, the corresponding fixed point for the cancer cells, again thanks to the constant population constraint. Namely, in this case, the total number of cancer cells will be 1 minus the total number of healthy. Okay, so very quickly we can resolve the fixed points for this equation. So I'm looking for fixed points now, And we know that this is going to be this value here. Okay? And basically we are all done. We could prove that this is actually a stable fixed point, which is what we normally look for. Naturally, this is going to be 1 minus c, and that's what I just was just saying. So here you could extract c accordingly if you wanted to. In order to show, though, that this is a fixed point, we're going to work a little bit different. We are not going to use either the potential function or the lambda or Lyapunov coefficient. We're going to do something actually different. We're going to take this solution and we're going to say, okay, what if I want to take this solution and move a little bit farther away from it? Okay, so now this is going to be a little perturbation around this value of n. And this is just a different method, but it works very elegantly sometimes, and I want all of us to be aware of the possibility to use this method. So here, basically, I'm introducing this epsilon thing, which only tells us that we are deviating ever so slightly from the equilibrium point, right? Well, now if I include this into this equation, what I see is that because I take the time derivative of n, and the time derivative of a constant, namely in this case the value of the fixed point is 0, here I could rewrite this as follows. The derivative of epsilon over time. Now on the right hand side I want to substitute n by this n star plus epsilon. Okay, so let's do it. If I substitute beta f minus alpha plus beta f, and here I write n star, let's write n star for what it is, which is beta f divided by alpha plus beta f, and then add this epsilon, as I am doing right here. So this is exactly doing this. Notice that this is going to cancel with this. The numerator is going to cancel with this denominator, and now beta f is going to cancel with the remaining beta f over here. So all that's going to be we are going to be left with is this. Great. So basically I now have an equation, let's write this again. I have an equation for this perturbation. I want to write it here. That I purposely put in the variable n over time here, or just take the variable n. We have perturbed it around its equilibrium point, and as a matter of fact, what we see here is that this perturbation is actually solved by an exponential function with decay rate alpha plus beta f. This means that if I were taking this seriously and I am actually writing what will happen to this perturbation according to my dynamics, I see that if I had an initial value for this perturbation, all I'll see is that this is decaying exponentially. Well, that's great, but what is this telling us? Well, as I said, this is yet a third method in order to obtain the stability of fixed points. And this is maybe a little bit more succinct in the sense that it's telling us exactly that this is going to be stable because as soon as I perturb my solution around the fixed point n star, and I use this perturbation and look at the value of this perturbation over time, and this is what I've done over here, I solve the value of this perturbation over time, I realize that the perturbation is going to decay. And this is because this is going to be sitting at the minima, right? And if I'm sitting at the minima, this is n star, and I have some perturbation over this side, for example, I know that this perturbation is going to come back to n star. Or if I perturb the system and put it up here, right? So this would be a negative epsilon. And this is also going to go back to the bottom of the well, right? So that's exactly the same thing that we have been exploring in the other two metaphors that we use in order to find out about stability. And we will use it later on in other contexts. So it's important that we bear this in mind. This is your point to make this example clear. Great. So the next thing that this problem asks from us is that we actually go beyond the fixed point paradigm and we actually solve excuse me, the total solution, the solution over time of the number of healthy cells. You can also do this for the number of cancer cells in whatever way you want. In this case, I am going to jump ahead and leave this as an exercise to you. Again, very briefly, what you have to do is you start with your equation, right, which I'm writing here for the nth time, bf minus alpha plus bf times n, and you want to solve this equation by separation of variables, considering some initial conditions. Okay, in this case, the initial conditions that I will use are the following. We will consider that at the beginning of this differentiation therapy, all I have in the system are cells of the cancer type, right? This means that n at 0 will be 0, right? Whereas, obviously, since all of the cells that I have are going to be cancer type, and I have a constant population constraint, this is natural that I get now C at 0 equals 1. In case that you want to solve also C of t, which I also leave as an exercise. However, I'm going to give you the solution for n of t. Using these initial conditions, we shall have this, the solution that you should work out step by step. Okay? Great. We're almost there. Let's just also draw here how this should look like, right? So this is going to be n t, this is going to be t, and basically what we're saying here is this is going to increase until we reach the equilibrium point. But now we have also found how is the functional form of this curve right here. The last part of the problem asks us about something that also occurs in cancer treatments, which is what happens when you get some resistance, when you have, through this process, you have selected cells that are no longer sensible to this sort of therapy, or even in other format, if you think about what happens if a time tau, right, if a t equals tau greater than 0, of course, I basically interrupt treatment. So let us actually consider this situation by actually taking that f is not a constant, but if you want is a function of t, but in this case we'll use that for t greater than 0 and smaller than tau, we can use smaller or equal than tau. The value of the pharmacological molecule or the drug concentration in the system is taken to be constant, whereas for t larger than tau is just dropped to 0, right? In this way, we know that this solution, it's still going to work for t between 0 and tau, right? Because everything is exactly the same as before. Only now, instead of f, we need to use f sub naught, which we're using here to differentiate this part of the problem from the previous one. Great. But at time tau, all of this f is turned strictly to 0. So what will happen when we do that, right? Well, we could just write down the solution straightforwardly for the total number of healthy cells, the n type, right, just by thinking a little bit about it. Right? So first off, what we have defined now implies that at this interval, this is going to be my solution. This is going to be describing how the total number of normal cell types evolve in the system over time. Beta f naught t, right? However, precisely at time tau, this reaches some value, right? As a matter of fact, at time tau, what we have is n of tau, which all you need to do in order to get n of tau is substitute for this function here, substitute here tau. We're going to call this n sub tau, but it's important to know that this is something that we can know from all the previous conditions that we had, because it's just a matter of substituting for the value of t accordingly. Great. So at time tau, there's no longer the direction from cancer cell to normal cell type. This has been taken away by the fact that we have interrupted the treatment. Okay, so now what does this mean for the rest of the system? Well, in this case now, if we remind ourselves of the differential equation, remember that we had here beta times f times c, and then we had minus alpha n, but now f is 0, right? And this is the actual equation that we shall get for t larger than tau. So now this is the equation that we need to solve for this part here. So for between 0 and tau, we already had our solution, but now for times larger than this time tau, this is the solution, and this is the equation that we need to work with. But this equation is pretty straightforward. Again, I'm going to be writing t larger than tau here, so there's no confusion, right? We know that this equation is its initial condition. Careful here, the initial condition is exactly the one that we were left off before we entered this regime, and then e to the minus alpha t. So this is our solution for t larger than tau. And now, considering these two, well, with this consideration and this one over here, we are describing all of the time evolution, right, for this number of healthy cells over time, considering that we will interrupt the treatment at time tau. And schematically, this shall look like something as follows. So here, we will consider that we are interrupting the treatment at time tau. This is time t. This is the total number of healthy cells. We have said that this begins like this, right? And it wants to saturate at n star, but it never reaches it. Let's actually do it a little bit better. Before reaching n star, the treatment is interrupted, right? So here we stop the treatment. And now what we see is exponential decay, right? N star should be up here, and this right here is n sub tau. Okay? And this curve, I'm going to do it again, is the curve of the total number of healthy cells that we should see in the system over time. That's the solution that this problem was requiring. Okay, so that's it.